Thanks for being on the call this morning. I'm excited to share with you guys this tool that I've been developing called molDscript, which stands for molecular descriptors, which is a Python tool that is designed to go from unstructured QM data to structured CSV files. So this aligns with CCAS because it is in the representations theme and the optimization and prediction thrusts. And I really want to start the talk off by kind of framing it under this big question within chemistry-based machine learning, which is how do we represent molecules? So you can see this toluene molecule here, and uh, humans are able to understand this really well, but we need ways to turn this into representations that um, machine learning models are able to also understand. So one way we might think to do that is through string-based representations, like this smile string here. But while this is still human understandable, it's not the most kind of machine understandable. Models require numerical inputs, whereas molecules are discrete objects. Kind of same with this string-based representation. So we kind of need ways to go from the structure to numbers. And one of the ways that we could do that is through the use of fingerprints or descriptors. So molecular fingerprints are these binary vectors that encode different portions of the molecule, and each spot in the vector is either a 0 or a 1. A 0 would indicate that that substructure is not present in the molecule, whereas a 1 would indicate that the structure is. So you can see in this kind of simple example here, we might have this benzene portion of the molecule as one of the spots in the fingerprint, and this methyl group as another spot. We can also think about encoding these as graph-based representations where all of the atoms in the molecule are nodes on the graph and the bonds are edges in the graph. And this has been shown to work quite well for like property prediction in machine learning. But you often need lots of data to be able to train these models. And you can also think about doing some sort of representation learning where you often start with one of those smile strings and through some computer learned process, translate that into a binary vector or some kind of numerical representation. You can think of things like LLM models as well as like variational autoencoders can kind of do this process. And that leaves, I think, one big area left for these representations, which is DFT-based representations using like QM features. So I think a really good example of this is in the Kraken database that was published a few years ago. So this is looking at phosphine ligands, and through this work, a bunch of QM descriptors and some other descriptors were curated for a big library of these ligands, and this has been shown to be really effective, and people have found a lot of use from this data set. But it would kind of really be great to have this for other substrate classes, because more recently, these DFT-based descriptors have still found a lot of use, even within the CCAS group. These are things that are able to represent molecules in ways that are really interpretable for us, which is something that I think is really important that we're making these interpretable models. But it's kind of difficult to curate them, and there isn't really a set kind of standard for how to do that or kind of general program to do that process. So I designed molDscript to be able to generate QM featurizations of molecules in a kind of high throughput general process with the hope that we would be able to develop these kind of libraries like Kraken for any kind of substrate class kind of on the fly. So moving into kind of what molDscript actually does. It takes outputs from a few of the major QM programs. So historically, people have been using Gaussian a lot, but more recently, programs like Orca and QChem have started to gain popularity. And designing this program, I really wanted it to be kind of agnostic to that. So you would be able to use your favorite QM platform and even do, say, optimizations in Gaussian and single points in Orca. And the program should be able to just handle that kind of on its own. Um, then from these DFT outputs, it curates a set of features. So here's just some representative features for molecule level. It's curating things like dipole moments and frontier molecular orbital properties. For the bond level, it's curating things like Weiberg bond indices and simple bond distances. And then for atom level descriptors, it's curating things like charges and Fukui descriptors, as well as on the fly calculating buried volumes. Then, once it has these features, it turns them into one of three CSV files for molecule level, bond level, and atom level features, which hopefully should be relatively plug and play into any kind of machine learning endeavor. And I know even here at CCAS, there's been a lot of work in this area of tool development, even for these QM featurizations. So I just wanted to kind of put into perspective like where I think molDscript fits into some of these other programs. So you can think about Morpheus, which I would say is really good at curating particularly steric descriptors of molecules. Um, and while I didn't use Morpheus in molDscript, you can potentially think of this as almost like fitting within molDscript, where you would use Morpheus to get those steric descriptors, and then also combine them with things like the like DFT quality homo-lumo gaps and things like that. You can also think about the Auto QChem package that was developed by the Doyle Group. And this is a really cool end-to-end smiles to DFT parameter and DFT dataset package. And I think this is kind of similar to what molDscript does, although molDscript starts from the completed DFT calculations. And what we really wanted was for it to be as general as possible so people could use like any different QM package, and molDscript should be able to work with it, as well as a bunch of different calculation types. And it's pretty modular, so if there are calculation types that aren't currently included in molDscript, they should be pretty easy to add in. And lastly, you could think of a program like Acme, which I think is best at the kind of smiles to DFT calculation pipeline, where you can start with smiles and it will embed the conformers and prepare DFT input files and then monitor these files completion to make sure that they all terminated properly. And molDscript, in a lot of the examples that you'll see later, I actually used Acme to create the DFT input files. But then molDscript is able to kind of in a high throughput fashion parse those DFT output files and turn that into kind of structured CSV file formats. And I think there's a lot of kind of big open questions about how best to do this DFT featurization of molecules. And an example of kind of, I think, a big lingering question is this idea of conformer dependence. So, in a recent paper by some CCAS folk, we can see that for some features, such as the volume of the molecule, if you look at these violin plots, going ligand to ligand, there isn't really much conformer dependence, and you can see that kind of by how narrow those bands are. Whereas other features like this sterimol B-min are quite conformer dependent. So for any ligand, you can have a big range of the feature value, which kind of brings up the question like, what should we do about that, and kind of how important are these conformers to consider when featurizing molecules? Um, is it okay to just use a lowest energy based representation, or should you use a Boltzmann weighted average representation of the molecules, or maybe even like a minimum, maximum, and range of a particular feature within a given Boltzmann population window? So I think there's still kind of open questions about how this data that was collected for bisphosphine ligands applies to other substrate classes, and how other properties are influenced by kind of conformational variability. So I really wanted molDscript to be able to try to tackle these questions on top of just curating those DFT descriptors. So here you can see a little demo on how to use molDscript. So I wanted it to be quite easy to use just through the command line. So we can see we're going to run it here on a set of 500 aryl bromides, and um, it's quite easy to run, and it will we'll have it running in the background here, and then going to look at kind of like a parallel data set that I had already ran molDscript on to kind of walk you through some of this stuff. So you might have mentioned in the previous tab, I used this arguments.txt file, and what that's doing is it's telling the program where to look for those DFT output files. So you want to structure it by putting them in folders by calculation type. So we have like an optimization, Fukui, NMR, and like population folders here. And then that arguments.txt file just points molDscript to those locations. And it also, you can specify like suffixes on the file names. So if all of your, say, NMR calculations end with underscore NMR, you can tell molDscript that, and it'll be able to automatically handle the conformer ensembles and curate the results from all the different proper or all the different calculation types into one. In this case, molecule level CSV, where you can see things like dipole, frontier molecular orbitals, chemical potential, electrophilicity, nucleophilicity, and then ionization energies and electron affinities. For the bond level, each bond has its own row in the CSV, so you can see the file name where it came from, and the atom 1 index and type, atom 2 index and type, and in this case, we parse the bond length and the bond orders. Similarly, for the atom level CSV, each row in the atom level CSV is one atom in the molecule. So we'll have the file name, the atom index, the atom type, and then things like charges, NMR shielding tensors, atomized bond orders, and then oxidized and reduced and Fukui values for these atoms. And lastly, molDscript will kind of save you these .dat files, which you can use to look back and see if there were any issues while it was parsing the data. And you can also see the CPU time that was used to calculate those or that like job type. It'll also give you the package use, the functional and basis set. And then in the case of Fukui, it picks what charge to use for the Fukui, and it'll let you know. So it will choose like natural charges over some of the others. But we can see jumping back here to the job that we started earlier. I I cut this a bit, but it really only takes a few minutes to run. So it'll tell us at the bottom here it took 380 seconds, so just a few minutes, and we're able to get all of these properties in nice CSVs that are kind of ready to use for machine learning. Um, and it also tells us the total CPU time for the generation of the data set. Um, so now I'm going to transition a little bit into some applications of molDscript. So the first one I'm going to show you guys is working with Dr. Groves and Dr. Camerota from Cal State Fullerton, and they had a data set of a little under 900 NHC ligands that they calculated, and they were interested in clustering it. So I used the molDscript parse representations and use all of the molecular level features as well as the atom level features at the nickel atom, which was shared among this data set. And you can see it seems to be working pretty well with 70% of the variance in the data set accounted for on these two principal components and some nice clusters that appear after we do this analysis. And kind of knowing that we can do this like PCA clustering based on these representations, I also wanted to look at an example of what conformer effects might have on this. So this is in collaboration with Dr. Graham Haug at CSU, and here he had conformers for his data set of 30 copper ligands, and I was curious what's the difference in the output that you get if you use lowest energy data versus Boltzmann weighted data. And with molDscript, you can do this just with a simple command line flag. If you do dash dash low E, you get the lowest energy data frame. If you use dash dash bolts, you get the Boltzmann weighted data, and you can just add both of these to the molDscript run, and it'll give you both of these data sets, which makes this kind of analysis, I think, quite easy. And for this small data set, you can see that going from lowest energy to Boltzmann weighted data didn't really change it too much, but it did change some of the points a little bit. And actually, in this case, one of these points changes from cluster 4 in the lowest energy data to cluster 1 in the Boltzmann weighted data, which probably isn't the biggest difference, but I think it does show that, I mean, there are tangible differences going from lowest energy data to Boltzmann weighted data, even for something like PCA clustering, which you might imagine might not be too sensitive to this. I also want to talk about this work that I've been doing with Abhijit from the Paton group. So you might remember his cascade model that he presented on a few months ago. We're working on expanding that model, and we took we calculated NMR tensors for these like 10,000 molecules, about 40,000 conformers using ANET2 generated structures. And I thought it was quite interesting. So what you're looking at here is the percent difference between the lowest energy and the Boltzmann weighted NMR shifts. And I think it's kind of interesting that for some atoms like nitrogen, we see a really big percent difference, whereas for other atoms like carbon and hydrogen, we see a pretty low percent difference between these two conformer representation models. And yeah, I think that's something that you might not have expected, and I think is interesting. And I'm still not quite sure exactly what to make of, but I think it just kind of shows that molDscript is able to just help facilitate this research being done kind of seamlessly. And lastly, another kind of lingering question I would say for these representations is the level of theory that you choose. So molDscript can also be helpful in doing research on this. So here you're looking at these centered kernel alignment values, which are uh, used quite a bit in the like machine learning computer science space to compare representations um, at different layers in, say, an artificial neural network. But in this case, we're just using them to compare the final representations that we get. So if the raw numbers are a little bit different, but they're still kind of scalable, it'll give a high centered kernel alignment value. And if they're truly just representing different things, we'll see a low centered kernel alignment value. So this is from that demo that you saw where we calculated ran DFT calculations for 500 aryl bromides using omega B 97XD in one of these three different basis sets. And you can see the cost breakdown here. MIDI is quite a bit faster than Def2 SVP, which is quite a bit faster than Def2 TZVP. And we get this all automatically from molDscript. And if you look the molecule level data, MIDI is quite a bit different in its representations than Def2 SVP and Def2 TZVP, whereas whereas those two are pretty similar to each other. And then for bond level and atom level data, all three of them are giving pretty similar representations of the molecules. So to kind of wrap it up, I just want to throw out the kind of help that I'm still looking for. So I'm interested if CCAS folk have some more DFT data sets to test this code on. They could be old or new data sets. I think just with trying to make it as general as possible, I want to be able to test it on as wide a range of calculations as I can. So the more I can test it out, the better. And then I'm also interested if anybody has any unique applications of the program that might be able to help kind of address lingering questions about how to featurize molecules using these QM featurizations. And I'd like to end by acknowledging my advisor, Dr. Paton, as well as the Paton and Kim groups at CSU, and then Dr. Groves, Dr. Camerota, Dr. Haug, and then Alex, LC, Grace, and Shabari for their help providing data and testing my program, as well as the NSF and CCAS for helping to fund this research.